For how many ordered pairs BC of positive integers does neither x squared plus bx plus c equals 0, nor x squared plus cx plus b equals 0 have two distinct real solutions? Okay, what does it mean for a quadratic equation to have two distinct real solutions? Well, let's take a look. If we use our trusty quadratic formula, we have for x squared plus bx plus c equals 0, that x is equal to negative b plus or minus the square root of b squared minus 4c all over 2. Okay, and the thing is, if you have something like b squared minus 4c, if it's greater than 0, the equation has two distinct real solutions. If it equals to 0, well then this thing becomes 0 and you have a double root at negative b equals 2. One real solution. And if it's less than 0, you have imaginary solutions. So we want how many ordered pairs b and c of positive integers. Do both of these equations not have two distinct real solutions, which means that this b squared minus 4c cannot be greater than 0 for either this nor that. And if you have x squared plus cx plus b equals 0, your discriminant, we call it, is c squared minus 4b, is right? So we want b squared minus 4c and c squared minus 4b to be less than or equal to 0. b squared minus 4c less than or equal to 0, and c squared minus 4b is less than or equal to 0. Ultimately, that's what we want to find out. How many ordered pairs of b and c satisfy that? And what we can do is we can actually split like our search for the solutions up into two cases. Case 1 is when b equals c, in which case b squared minus 4b is less than or equal to 0. That's what both of these equations become. What does that mean? It means that for, let's say, b squared is less than or equal to 4b. And since b is positive, you can divide both sides by b to get b is less than or equal to 4. Right? B is a positive integer. So b is equal to 1, 2, 3, 4, and c is equal to b is equal to 1, 2, 3, and 4 respectively. So this case gives us 4 solutions: 1, 1, 2, 2, 3, 3, and 4, 4. Okay, now case 2. Case 2 is when b is not equal to c. In which case we have either b is less than c or b is greater than c. So without loss of generality, b is greater than c. And we can multiply our count by 2 for b is less than c because those are essentially identical. So b is greater than c. Well then, b squared minus 4c is less than or equal to 0. C squared minus 4b is less than or equal to 0. This implies that b squared is less than or equal to 4c, and c squared is less than or equal to 4b. Okay, so now what we see is, okay, b is greater than c, which means that b squared is greater than c squared. Because both of them are positive, it's okay to take squares, right? But b squared is less than or equal to 4c, right? So 4c greater than or equal to b squared, which is greater than c squared. So c has to be strictly less than 4. So c can be either 1, 2, or 3. Okay. If c is equal to 1, you have b squared is less than or equal to 4, right? And since b was greater than c, b has to be 2 or greater. So the only solution for c equals 1 is b equals 2. If c equals 2, b squared is less than or equal to 8. But what does that mean? B would have to be greater than c. So b essentially has to be 3 or greater. But that none of those work because 3 squared is 9, which is greater than 8. And as you go higher and higher for b, the b squared becomes higher and higher. So no solutions for B if C equals 2. And if C equals 3, that's even worse because B squared is less than or equal to 12 and B is greater than 3, no solutions either. So when B is greater than C, 2, 1 is a solution. And similarly, if B is less than C, 1, 2 is a solution. And those are all the possible cases, which means that our total count for distinct real solutions is 6. So our answer is B. Thanks for watching, and we'll see you next time.